Okay, hi. Welcome to Recitation 5 for Econ 184. My name is Tiger. So let's talk about uh, your quiz 1 explanations. So a little bit statistics for your quiz 1 before curve. So the mean score is out of 35. The mean score is 26.43, and the standard deviation is 5.47, and median is 28. Max is 35, and minimum is 6.5. So to save time, I will explain the questions that people usually misunderstand. And remember that everything in econometrics is cumulative. So it even requires a solid understanding of statistics. Otherwise, you simply cannot fully appreciate it. So, 4 credit course should require 4 classroom hours and 8 hours out of 8 hours of out of class hours each week. I'm not sure if there is a curve for this quiz. Okay, so let's uh, check out the PDF. So part one is multiple choice. I think we have 5 questions, right? 2 students got all 5 questions correct. Um, so number 2 is so that it asks you the arrow term UI is defined as which one? The answer is C. Right? The arrow term is from the population, like the data generating function, not your estimation, not your regression, not from your estimation equation. So this should be C, right? Everything is in population. These are population parameters, beta 0, beta. So there's no hat. And number 3 is to obtain the slope estimator using the least squares principle. So I think this is OS, right? You divide it should be C, right? Sample covariance of X and Y by the sample variance of X. So if you cannot derive at least a single variable regression case, so you should try to remember this, because least square of what, at least you should try to or remember or know how to derive. And so for example, your beta 1 is here, so covariance of X and Y over variance of X. The slope estimator beta 1 has a smaller standard error, other things equal, if there is more variation in the explanatory variable. So intuitively, if you have a more variation in X, you should get you should have a higher chance to get a good estimation of your coefficient on this variable, right? So it's only A is possible. If you want to learn the mathematical formula, here is how you here's your standard error equation for beta 1 estimator. So you see here, if you have a more variation, means the bottom term, this variance is going to be high, right? So the overall standard error is gonna decrease. And we use the top part, like a square root of your square residual over n minus 2 to estimate your variance of your error term in the population. So n minus 2 means you have degrees of freedom of n minus 2. And most students got part 2 right. So we'll skip part 2. And part 3 is very important. So earnings and education. We regress basically your education level on average hourly earnings. I think only one student got the full score on this one. Congratulations to her. So assume that you have a collect a cross-sectional data for our average hourly earnings, the number of years of education, and gender of the individuals. So you code individuals as 1 if they're female and 0 if they're male. You have all the 3 variables. And first you regress your hourly earnings on education level. And then you have R square, SER, observation, how many observation, and the standard error for your estimated coefficient. Okay, so first one, most people got SER wrong. So SER is the standard error of the regression. It's a measure of fit, and it's calculated using standard deviation of the residuals. So the average size of the residuals is $9.3. And I think except one student, I think Hattie, yeah. So except Hattie, everybody got economic significance wrong. So economic significance is not statistical significance. They're 2 different things. So they're they're not that much related to each other. So you have 2 methods to calculate economic significance. So one is using elasticity. So basically, we can calculate the elasticity at the means to understand the percentage change in earnings for a percentage change in education. So 1% change in education will lead to how many percentage change in earnings. So we don't have the mean value, right? We don't have the mean value, so we cannot calculate economic significance in this way. And the second method is to use standard deviation. So if one standard deviation change in x leads to more than usually 0.2 standard deviations changing in y, then we say this x is economically significant. But there is no consensus on this, whether it should be 0.2 or 0.3 or 0.5, whatever. But we don't have this standard deviation. So in your answer, you should say we don't have mean or we don't have standard deviation, so we cannot calculate economic significance. This has nothing to do with the statistical significance. Part C, being a female, you wonder how these results are affected if you enter a binary variable female, so which takes a value of 1 if the individual is a female. And you add this, the result is here are your standard errors, coefficient, new R square, SER, and so it asks you interpret coefficient, statistically significant, does it make sense? Standard error of the regression decrease, well, the regression R square increased. So we'll check part D. The coefficient on education variable is roughly the same magnitude as we saw earlier. Why? So this one is asking you for what are the source of your omitted variable bias. You should have an understanding of your omitted variable bias to do this. So here we know 2 facts. One, the effect of female on average hourly earnings is not 0. It's not 0. And 2, the coefficient, and it's very statistically significant, right? And also the coefficient on education variable is roughly the same. So this is because female is associated with earnings, but female is not correlated with education. The education is similarly distributed among these 2 groups. Okay, that's basically all I gotta say for your exam. And let's talk about something about your R code. Okay, so my next topic is perfect collinearity. So if you put two dummy variables that are perfectly uh, linearly related, if they're if you put both of them in your regression, what will happen? So first you load the data, and you load the packages, LM test, sandwich, stargazer, right? And you use here we use the AER data, so we get the CPS. We call the data CPS, right? And our first regression model is we regress earnings on age and education. So here we can see the coefficient on age variable is positive. Both coefficients are positive. Both are very, you see 3 stars, very statistically significant. So age and education should have a positive significant effect on, sorry, not seeing effect, impact or association, yeah, positive association with earnings. And we can use a coef test to get the robust standard errors. Remember what heteroscedasticity robust standard errors are. And you see they're still very significant, 3 stars, even at 1% level, right? And now you create 2 dummies, one for female, one for male. And you can see if you use model 2, model 2, you can, if you include only one gender dummy variable, you can see you can get negative 3.7, very significant. So basically, on average, male got $20, $20.1 on average, and female got 3.75 less average hourly earnings than male got on average, holding other factors constant. And see what will happen if we include both male and female dummies. You can write earnings, regress earnings on both the dummy female and dummy male. And this will give you a similar result. So we cannot see the coefficient for dummy variable male. So R will drop one dummy variable for you. So to avoid perfect collinearity. And also you can add a little 0 here. See, we don't have a 0 here, and you add a little 0 here to drop the constant term. So drop this constant term. Now you can see both coefficients are positive, right? So this gives you this gives you, so for male on average the earning is 20.1, female the wages on average is 16.3. So the difference between these two are your coefficient before you're dropping the constant. It's the difference. And then you can add other control variables like age, education, everything here. Okay. After controlling for age and education, on average, female will earn like 4.25 less than men will earn. And next, we can talk about the joint hypothesis testing. So remember, this is your F test. We can test if so before you use t-test to test whether one coefficient is equal to a certain number. Now we can test if 2 coefficients are equal, or they're both 0, or they're both 1, or whatever. Yeah, so basically here we load our California schools, and we regress the student test score student-teacher ratio, and I think this is expenditure per student, and this is English learner percentage of English learner. So if you have a high percentage of English learner, you should have a lower score. If you have a large class size, you should have low score. If you have a high expenditure per student, you should have a higher score. Right? So the coefficients make sense. And we can get the robust standard errors using coef test. Code is here. And then you can add the robust standard errors to Stargazer using this, doing this way. So you first find the standard error for model 1. So you use list square. Use this one to calculate. Basically, calculate. You can just copy and replace your model name for this model 1. And then you add SE, the option SE equal to here, your SE model 1 to your Stargazer. And you will see it will report you robust standard errors in the parentheses. Now we can test null hypothesis is beta 1 is 0 and beta 2 is 0. So student teacher ratio is 0 and expenditure per student is 0. Anyway, and first, if you do not say anything, this gives you the homoscedasticity only f. So it means everything is homoscedastic. So this f stats you can only use when homoscedasticity holds, and this is usually not true. So you can see you got a very significant p-value here. So we can tell at least one of them is not 0. I can reject, right? You can reject the null hypothesis. And this will give you the heteroscedastic robust standard error. You should always try to use this code. You can have the options here, so it's very convenient. So the only difference is you add this part. And then we can test the null hypothesis. So beta 1 equals to beta 2. So in this case, we do not restrict them to has to be equal to 0. You can like beta 1 and beta 2 can be anything, but they have to be equal to each other. Okay, so here you have CA, student-teacher ratio equal to CA, expenditure per student. And now you see you cannot reject the null hypothesis. So you cannot reject this one. It's very likely that the coefficients are equal. Okay, that's recitation 5.